Hello and welcome to Controllers Tech. Several years ago, I created a comprehensive series covering Modbus RTU implementation for STM32 microcontrollers. Throughout that series, we explored how to configure STM32 microcontrollers to function as both Modbus master devices and Modbus slave devices. We also demonstrated various practical operations, including how to read and write holding registers and coils, as well as how to read input registers and discrete inputs. Now, I am launching a new series focused on Modbus TCP for STM32 microcontrollers, which uses Ethernet connectivity. For this series, I will be using the Mongoose networking library, which includes a built-in implementation of the Modbus protocol. This built-in support allows us to concentrate our efforts on developing the application logic and functionality, rather than implementing the protocol from scratch. This introductory video will provide you with a clear understanding of how Modbus TCP operates, and explain the key differences between Modbus TCP and the Modbus RTU protocol we covered previously. We will examine the structure of the Modbus TCP frame that is transmitted over the TCP protocol, and we will understand how this frame is constructed using practical, real-world examples. Starting from the next video in this series, we will begin our hands-on implementation work. First, we will configure the STM32 microcontroller as a Modbus slave, which operates as a server in the network. Following that, we will configure the STM32 as a Modbus master, which functions as a TCP client that communicates with the server. I have prepared a comprehensive PDF document that contains important information, and detailed explanations about the Modbus TCP protocol. I will provide a link to this PDF in the video description below, so you can download it and refer to it as needed. The Modbus protocol is fundamentally built around an application data unit, or ADU, which contains all the information we need to transmit through the TCP protocol. This ADU is made up of two main components: first, an MBAP header at the beginning, followed by the function code, and the actual data that needs to be transmitted. Together, the function code and the data form what is known as the Protocol Data Unit, or PDU, which works as a single unified package. Before we can send any information over TCP, we must first construct this complete application data unit with all its required components. If we compare this to the Modbus RTU frame structure that we used previously, we can see some important similarities and differences. In the Modbus RTU frame, the structure included an address field at the beginning, followed by the function code, then the data to be transmitted, and finally a checksum value at the end. In the Modbus TCP frame, the address field has been replaced with the MBAP header. The function code and data remain exactly the same as they were in the RTU version, so you will be familiar with how we handle them. However, there is one significant difference: Modbus TCP does not use a checksum, because the TCP protocol itself already includes error checking, and a checksum mechanism built into its own frame structure. This means we don't need to add our own checksum calculation. Now, let's examine what the MBAP header contains, and learn how to properly construct it for our Modbus TCP communications. The first 2 bytes of this header are the Transaction Identifier, which is a unique ID generated for each request by the Modbus master. This field is initialized by the client because the client will send a request to the server, and this request will contain this unique identifier. When the server sends the response back to the client, this identifier is used exactly as it was received. Basically, it is copied directly from the client request, and then transmitted back to the client without any changes. The next field consists of 2 bytes called the Protocol Identifier, which always remains 0 for the Modbus protocol. This field is also transmitted back by the server without any modification, just like the Transaction Identifier. Next is the length field, which is also 2 bytes in size. This length field represents the total number of bytes that will follow after this length field itself. This count includes the Unit Identifier, plus all the bytes present in the protocol data unit part. We will see in a practical example later how this length is actually calculated. However, when the server sends a response to the client, the server calculates its own length value based on its response data, so this part is not copied back like the previous fields. Instead, the server creates a new length value. The last field in the MBAP header is the unit identifier, which works very similarly to the slave ID that we used in the RTU protocol. This unit identifier is especially useful when there are multiple servers present on the same network. However, if you are connecting your master with just one server, then this field does not really matter much. The server will copy this field when it is sending the response back to the client. You can read more detailed information about these fields in document that I will leave in the description of this video. One important piece of information to remember is that all Modbus servers must be registered to listen on port 502. The server must be actively listening on this specific port for incoming connections. Additionally, all the different fields in the Modbus TCP frame are encoded using Big-endian format. This means we need to keep this in mind whenever we are extracting data from the frame, or combining multiple bytes together. Now let's look at a practical example of how to construct a Modbus TCP frame when we want to read the status of coils. First, we need to construct the MBAP header step by step. The first field consists of 2 bytes and is called the transaction ID. As I mentioned earlier, the client sets this field to a unique value for each request. In this example, we are setting it to 1. Since this field is 2 bytes wide, we need to send the higher byte first, because all the fields are encoded in Big-endian format, which means the higher bytes must be sent before the lower bytes. The transaction ID is immediately followed by the protocol identifier field, which is always set to 0 for Modbus communications. This field also occupies 2 bytes in the header. Next comes the length field. This length value represents the total number of bytes that will follow immediately after this length field. If you look at what comes after the length field, we have 1 byte for the unit identifier, 1 byte for the function code, 2 bytes for the starting address of the coils, and 2 bytes for specifying the number of coils to read. When we add all these together, we get a total of 6 bytes. Therefore, the length field should be set to 6. After the length field, we place the unit identifier, which the client can set to any value for basic operations, since we are assuming there is only one server connected to the client. However, if you have multiple servers on your network, you must set the correct unit identifier for that particular server. Inside the Modbus slave device, you can implement a filter mechanism, where a particular slave will only respond to queries that are transmitted with its assigned unit identifier address. This completes the MBAP header construction. Now we will move on to constructing the protocol data unit, which consists of the function code followed by the request data. To read coil status, we need to use function code 1. The data section contains the specific parameters for the coil reading request. This will include the starting address from where we want to read the coils, which requires 2 bytes, and 2 more bytes to specify the number of coils, basically, how many coils we want to read from that starting address. In this example, we are requesting the server to send the data for 4 coils, starting from address 0. When the server receives this request from the client, it will send a response back. This response will again consist of an MBAP header followed by a protocol data unit, just like the request. The MBAP header that the server constructs will remain basically similar to what the client sent, except for the length field. The server must recalculate the length field, because it needs to send the requested number of data points back to the client, and this can result in a different length value. In this example, the total length sent by the server is 4 bytes. This consists of 1 byte for the unit identifier, 1 byte for the function code, 1 byte for the count of data bytes, and 1 byte for the actual coil data. So now you should understand how the complete communication process works. The client sends the request with all the necessary parameters, and when the server receives that request, it processes it and sends back a response, containing the data that the client requested. Here are the different function codes that we will be using throughout this series. We have specific function codes for reading coil status, reading holding registers, reading input registers, writing a single coil, writing a single register, writing multiple coils, and writing multiple registers. There is also a function code available for reading the slave ID information from the server. Now, let's look at a practical example using actual Modbus TCP client software. I'm going to demonstrate using the simple Modbus TCP client for this series. This software is free to use, and we used similar applications in the Modbus RTU series as well, so it will be easier for me to work with and explain the concepts. At the top of the interface, we have to set the mode to TCP, followed by entering the IP address and port number of the server we want to connect to. Then we have to provide the slave ID field, although I should mention that it does not really matter what value you enter here if you are connecting the client to only one server. Next, we need to set the function code. I'm using function code 1 to read the coil status from the server. In the first coil field, we have to provide the address of the first coil we want to read. Note that the addressing for the coils typically starts from 0, but here it is set to 10,001. Do not mind it, as we will cover it properly in the later video. The offset is also the same, so the actual address is anyway 0. The number of coils field specifies how many coils we want to read starting from that address. Once we set all these parameters correctly, this generates the actual request that the client will send to the server. Now let's analyze the actual request data that gets generated and transmitted. The first 2 bytes of the request are the transaction ID. This unique ID, 0x01, is generated by the client for this specific transaction. If I were to perform another transaction, the client would automatically generate a new ID by default. Next are the 2 bytes representing the protocol identifier, which always remain at 0 for Modbus communications. Then we have the 2 bytes of the length field, which is set to 6. If you look at the bytes that follow immediately after the length field, you will count exactly 6 bytes in total. Next comes the unit identifier, which is the slave ID value. We set the slave ID field to 10, so that same value of 10 is being sent here in the request. Following that is the function code, which is 0x01 because we are reading coils. This is followed by 2 bytes representing the starting address, which is 0 in this case. The reason it is 0 is because our first coil address and the offset address are the same value, so they basically cancel each other out when subtracted. Finally, we have 2 more bytes that specify the number of coils to read, which is 4 in this request. Once the client sent this complete request to the server processed it and responded back with the coil data. Here you can see the response that was generated by the server. On the top right of the display, you can see the 4 bits of coil data that have been received and logged at the requested address. In this case, they are all zeros because I was simply testing the system, so I set the values to 0 for demonstration purposes. The response from the server consists of similar structure to what the client sent. It starts with 2 bytes of transaction identifier, which is copied from the client request, then 2 bytes for the protocol identifier, which also remains 0. The next 2 bytes are for the length field, and importantly, the server's length field has a different value here, because the server is only sending 4 bytes after the length field. Then we have the unit identifier, followed by the function code, and then the byte count, which indicates the number of bytes of actual data being sent, which is 1 byte. Finally, we have the actual coil data itself, which is 0. This is the complete process of how Modbus TCP communication works. The client, which acts as the master, sends a request to the server. The server then performs the requested operation and sends a response back to the client containing the requested data. In this series, we will also see this communication working in a practical, real-world scenario. The good part about using the Mongoose library is that we do not need to manually handle all the basic protocol details. All the response frames will be automatically created by the Mongoose library itself. We only need to write the application-specific functions. For example, if the server receives a request for coil data, we just need to write functions that provide the coil data to the response. The rest of the frame construction, including the MBAP header, function codes, and all the protocol details, will be handled automatically by the Mongoose library itself. We will see exactly how this works throughout this series. I will also create a Modbus TCP series using LWIP as well, but that implementation will come in the distant future. For now, we will focus exclusively on the Mongoose library, and we will also see some live demonstrations of how everything works together. We will even implement an HTTP server so you can see the live demonstration of all the fields that we will be working with in real time. So I hope you now have a clear understanding of the basics of the Modbus TCP protocol. I strongly recommend that you review the Modbus RTU series as well, because it will be much easier for you to understand the TCP protocol, if you already have a solid understanding of the basics of how the function codes and data transmission work. The key point to remember is that the only change between RTU and TCP is the construction of the Modbus frame itself. The internal working principles and logic remain exactly the same. That concludes this introductory video. In the next video of this series, we will start the practical implementation by setting up the Mongoose networking library, and begin configuring the STM32 microcontroller as a Modbus TCP slave. You can find the PDF link in the video description for additional reference material. If you have any questions or doubts about the concepts covered, please leave comments below. Keep watching, and have a great day ahead.